Hi everyone. In this video we're going to go over the following objectives. Now don't worry about that noise you hear in the background, it's just a photocopier, so try to power through. Okay, the objective: describe why some atoms need to share pairs of electrons with other atoms. 2. Compare single, double, and triple bonds. 3. Compose chemical formulas for covalent compounds, which we also call molecular compounds, and for what is meant by the term diatomic element. Alright, so objective number 1. Describe why some atoms need to share pairs of electrons with other atoms. And for that, let's inspect our periodic table. Here we have these nonmetals. Now these nonmetals, they like to gain electrons. Let's take an example of, let's try to straighten this out here. Okay, let's take an example of nonmetals right in this region here. Now remember, forget about these. These are nonmetals, but they are noble gases. And noble gases have that stable octet, which means they tend to be non-reactive or inert. But let's take a look at, let's just say, fluorine. Fluorine has an electron configuration of 2-7. Well, what if it comes in contact with another fluorine? How is it that this outer octet is going to become stable? Let's go to the next slide and draw it out. Alright, so we have an electron configuration of chlorine as 2-7, and let's put another one 2-7. How is it that they are going to help each other become stable? Now, what might actually help better is drawing the dot diagram for chlorine. And there's one chlorine with 7 dots, because that's what it shows on the valence shell. And I'll do another chlorine, but this time I'll use X's. That way we could discern the difference. And if you notice here, if we actually slid these into each other, so if we actually took this and slid it into there, it would look like this. So here are the 7 dots for the outermost electrons for that one chlorine, and here it is for the other one. Now, the way to tell if, in fact, this does work out is we put a circle around this chlorine, and we count 1, 2, 3, 4, 5, 6, 7, 8 electrons, which would stabilize the octet, or stabilize the valence shell for that chlorine. And let's take a look at the other one. Put a circle around this one and count once again. 1, 2, 3, 4, 5, 6, 7, and 8. So here we have a situation where 2 chlorines joined hands in a way in order to help each other stabilize their octet. So here we have 2 nonmetals. So nonmetal bonded to another nonmetal. And what we call this is, we call this a covalent bond, creating a molecule. Now let's take a look at a few other examples. Here we have one hydrogen atom with its 1 valence electron, this other hydrogen atom with its valence electron, and when they join together, you see that they are now sharing 2 electrons, and this is now considered a diatomic element. Let's slide up and take a look at another example. Here we have fluorine with its 7 valence electrons, 7 valence electrons. Here's what happens when they combine. They're now sharing these 2 electrons. Remember, ionic bonding, they actually have a situation where electrons are transferred from one element to another, from one atom to another. Here's another example. Here are 2 different atoms. Here's oxygen with its 6 valence electrons and carbon with its 4. Now, how is that going to work out? Well, it turns out it works out in this fashion. They are actually going to share 2 sets of valence electrons. And let me do that circle test again on this one. So if we were to circle this oxygen, we can count out 1, 2, 3, 4, 5, 6, 7, 8. That oxygen atom is stable and happy. Let's look at the other oxygen on the other side. Again, 1, 2, 3, 4, 5, 6, 7, and 8. It is happy. And what about the carbon? Count them out, and we have 1, 2, 3, 4, 5, 6, 7, and 8. So each of these atoms is now stable because they are sharing electrons. Let's take a look at this last example here, much more complicated. Here we have fluorine and carbon. Looking at this carbon, it needs somehow to share 4 electrons, and each fluorine has the ability to share one of its. So the circle test. This fluorine, now sharing a single pair of electrons, is stable. If we count it out, 1, 2, 3, 4, 5, 6, 7, 8. 8 valence electrons. Two of these electrons are being shared. If we take a look at the other fluorines, I'm not going to circle them. That fluorine is the same as the first, this one, and this one as well. But let's circle the carbon and count it out. 1, 2, 3, 4, 5, 6, 7, 8. That carbon is now stable because 8 valence electrons. 4 of the electrons, these orange ones, come from the carbon itself, while the other 4 come from the 4 fluorines that it is bonded to covalently. Alright, objective 2, we're going to compare single, double, and triple bonds. Let's first take a look at the definitions that I put together, and then on the next slide put it to use, take a look at what it can look like. Alright, single bonds. When 2 atoms share one pair of electrons, so 2 electrons are being shared to satisfy both of their valence shells. Double bonds. When 2 atoms share 2 pairs of electrons, which is 4 of them, to satisfy both of their valence shells. And triple bonds. When 2 atoms share 3 pair of electrons, 6 of them in total, to satisfy both of their valence shells. If you see a theme here, they're trying to satisfy their valence shells. So now let's take some examples of a single bond, double bond, and triple bond. Here we have a classic single bond. Let's take a look down below at hydrogen. Now this hydrogen would take with it this 1 dot in its valence shell, while this hydrogen brings this 1 dot electron in its valence shell. And the only way that they can work together to satisfy both of their valence shells is to combine and share these electrons. Now think of these electrons briefly. These 2 electrons at any given moment both might be circling in orbits this one hydrogen, while these 2 electrons could be circling that hydrogen instead at any given moment. But then again, it could be 1 electron circling this one and 1 electron circling this one. It doesn't really matter, the electrons are being shared by both. Now take a look at this illustration just above it, and it has a dashed line. So if we were to look at this picture and this picture next to each other, we'd have to come to the conclusion that this dashed line represents 2 electrons. Now let's go ahead and take a look at a double bond. Now a double bond, here's a classic example. 2 oxygens need each other in order to satisfy the octet rule, the valence shells. This oxygen brings with it 6 valence electrons. So we got 1, 2, 3, 4, 5, 6, while this oxygen brings with it 1, 2, 3, 4, 5, 6. Now the only way that they can satisfy each other is to share 4 electrons. So that's 2 pairs. Let's go ahead and circle this and see if it pans out. We have 1, 2, 3, 4, 5, 6, 7, 8. And on this one, we have 1, 2, 3, 4, 5, 6, 7, 8. So each oxygen does have at any given moment 8 valence electrons because they are sharing 2 pairs. The illustration just above this shows 2 dashed lines representing 4 electrons are being shared. So this is a double bond. And lastly, a triple bond. This nitrogen carries with it 1, 2, 3, 4, 5 valence electrons, while this nitrogen 1, 2, 3, 4, 5 valence electrons. The only way that they could complete their valence shells is by sharing 6 electrons. Counting it out, we've got 6 in the center, 7, 8, 6 in the center, 7, 8. Again, they are sharing 6 electrons, which is 3 pairs, which is 3 dashed lines. This is a triple bond. Now keep in mind, atoms don't always bond with their other like atom. Sometimes they join with other atoms. Let's quickly take a look at that. So here we have an example of hydrogen with its valence electron and chlorine with its 7 valence electrons, giving it a configuration that kind of looks like this. All right, they are sharing 1 pair of electrons. We could also look at perhaps oxygen and sulfur. So oxygen and sulfur. Sulfur has 6 valence electrons. If you don't believe me, look it up. So there's 1, 2, 3, 4, 5, 6, where oxygen also has 6. So 1, 2, 3, 4, 5, 6. So here we have a double bond between oxygen and sulfur. And we could also take a look at, which one do I want? Nitrogen and phosphate. Nitrogen with its 1, 2, 3, 4, 5. Okay. And here 1, 2, 3, 4, 5. So we end up with a triple bond here. So how do we write these formulas now that we figure out how many of each? Let's take an example. We have 2 hydrogens and 1 oxygen become H2O. And that's what this looks like here. We have a single bond between this hydrogen and this oxygen, this hydrogen and this oxygen. That could be written also as this. Okay, in order to make nitrogens and hydrogens stick together to satisfy their last shell, their valence shell, we need 3 hydrogens to 1 nitrogen, and it looks like this. Of course, we could put the dashes in place of the paired electrons, and that formula is now NH3. And in order for hydrogens and carbons to fit together and satisfy their valence shells, we need to have 4 hydrogens to 1 carbon. It looks like this, and again we could have that dashed line. So what we do is we try to satisfy all the valence electrons. We look to see if maybe a single bond works, a double bond, maybe even a triple bond. Treat it like a puzzle, fit them together, and then you write the ratios. So for instance, again, H2O, 2 hydrogens to 1 oxygen, 1 nitrogen to 3 hydrogens, and 1 carbon for 4 hydrogens. Alright, now what is meant by the term diatomic element? Let's take a consideration of hydrogen. Hydrogen has with it 1 valence electron. In order for it to become stable, if there's another hydrogen present with its valence electron, it will join with it. It will chemically combine, but this is not a compound. Remember, the term compound means 2 different elements chemically combining. These are the same, so this is a diatomic element. Oxygen is also a diatomic element when it is in the O2 form. Nitrogen, the same. So that's N2. There's a triple bond there, but it's 2 nitrogens. It is a diatomic element. But conversely, if we have nitrogen bonding with phosphorus, now in previous video I said phosphate for the P, please, it's phosphorus. Triple bond, this is a compound, 2 different elements. So again, diatomic element means 2 di of the same element chemically combined.